Hey, welcome to Differential Calculus Part 2. I think you're going to like this because in this little presentation now, we're going to look at rules for getting the derived function or the derivative and not having to do all that algebra involved in the first principles method that we've just been doing. So you'll only use first principles if you are asked to prove or particularly asked to use that. Otherwise, we're going to try and develop rules to do it more quickly with any particular function. Let's have a look at their notation here. If we call the function f of x, we know the derived function or the derivative has got the symbol f dashed. Mentioned at the end of the last presentation though, was if the function is y equals, we would usually use dy by dx. We can use y dashed. And we say that dy by dx, it's actually not a fraction, it's not d times y over d times x. Why would we say that? Because if we have a symbol for the derivative, we have a symbol for the limit as delta x tends to naught of the slope of the chord coming into tangency. So this is a very big point. This is not a fraction. It's representing quite a complicated process of limit finding. So it's important that you say, well, it's a derivative of y with respect to x or anything that we're finding the derivative of. So it's an alternative symbol, as mentioned back there in that last presentation when we're looking at the Casio finding a value for the derivative. All right, so if we come down now, we already have some idea of some rules from our work with first principles so far. First of all, if the function is a constant, its derivative is 0. Let's come up here and have a look if we believe that. So here, this is supposed to be parallel to the x-axis. That would be y as a constant. What is the rate of change of y with respect to x? Or what is the slope of the tangent to this graph? The slope is 0, so its derivative is 0. I don't know, did you spot when you were doing first principles on x squared and x cubed that x squared was 2x, x cubed was 3x squared? So there's a rule. It's the power out the front times x to the 1 less power. We want to prove that in a minute. Now, I don't think Hayes and Harris do that one. It's beyond the level of this course to actually have to prove any of these. But I think it's interesting. So again, I'm taking screen clippings from Hayes and Harris, so you might have a copy of that handy by. If you have a function multiplied by a constant, it's actually the constant times the derivative of the function. We're going to go down and look at their proof for this. And if you have two functions added, you do the derivative process to each one. So can you see what we're doing? We're trying to break functions down and use rules to find the derivative rather than first principles. So let's come down a bit here. So the first one is this one here, where the function is a constant times the given function, and we want to prove its derivative is just the constant times the derivative of the function. Always start off with your fundamental definition, substitute in the function, so it's cu of x, so it's cu of x plus h, take cu of x, f of x plus h, take f of x, and of course we can factor out a c. And then we can say, well, the limit as h tends to naught of c is just c. It's independent of h. So as h tends to naught won't affect c. It will stay out the front. And then we've got this limit, which we recognise as u dashed x. So that's as required there. We have actually shown what was asked, which was to show that the derivative was that. Okay, so let's come down a bit to this next one now. This is the sum of two functions. So if we do that, always start with the definition. Limit as h tends to naught of fx plus h, take f of x on h, and then putting in the sum function. There it is, u of x plus h plus v of x plus h, minus the function u of x plus v of x. Let's group them up because we know certain pairs are useful. So here, let's put the u of x with the u of x plus h, and group up the v of x plus h with the v of x there. Oh, there it is there. Put those two together, because then what do you notice? We've got the limit of two things added, so they've both got to be divided by h, so there's the first one, plus there's the second bunch, divided by h, and therefore we recognise this as u dash x and v dash x. So that's what we were required to show. We could put as required there. All right. What about another one? Now, Hayes and Harris don't actually put this in there. What about f of x equals x to the n, which we've already mentioned to you? What about this one? Let's see if we can make something of this. Always start with the definition. Limit as h tends to naught of f of x plus h. Take f of x over h. Okay, let's put in our particular function. It's a limit now as h tends to naught of f of x plus h. Let's just check it. This is going to be x plus h to the n. Take x to the n on h. Oh, binomial expansions here. Do you remember Pascal's triangle work, perhaps? So this is Cn naught x to the n plus Cn1 x to the n take 1 by h to the 1 plus Cn2 x to the n take 2 by h to the 2. Do you see the pattern? Decreasing the power of x, increasing the power of h, and so you'll go right up to Cn no x's and h to the n. So that's our x plus h to the n using Pascal's triangle. Well, not really. I mean, it's using a binomial expansion. And these combination coefficients, I don't know how much you know about those. The numbers in Pascal's triangle, they are defined by CNR. So let's have a look. I think we'll put it over here. CNR is n factorial over n take r factorial by r factorial. So they are the entries in Pascal's triangle. That's a bit beyond this course. Let's go on with this one now. The limit as h tends to naught. Now Cn naught, the outside entry of Pascal's triangle, is just 1 x to the n, plus we will then leave all these others there. We're not going to play with those for the moment. And see what we've got right up to Cnn h to the n take x to the n. So you can see here, x to the n's will disappear. Now let's try to factor out an h, because we know we want to cancel that because of this denominator here. So let's take h out the front. Cn1 x to the n take 1, that h will go. The next one is Cn2 x to the n take 2. One h has gone out the front, so all these will lose an h, down to Cnn h to the n take 1. One less h in each term, including the last one. And then we can, what can we do? We can cancel, provided that h is not equal to naught. So we're saying we're looking at not an identical function. This one's got a point discontinuity, but we just sort of try to cancel the h out. But what we're saying there is right up to h equals naught, the limit of this new function is the same. So let's put this down now. Cn1 x to the n take 1 plus Cn2 x to the n take 2 times h. And all of these terms here still have an h in them. Okay, and that's important now, because the limit as h tends to naught of all of these here will tend to naught because they have an h in them. When you sub h is naught, they disappear. So the limit is this. And guess what Cn1 is if you go back up here? If you know anything about those combination coefficients, it comes to n. And we have proven it. That's as required. So I don't know whether you know much about the combination coefficient, but you could say, well, I know that in Pascal's triangle, the second entry in, which is n1, the second entry in always equals the n value. So you could think of it that way. N is 1, n is 2, n is 3, and the expansions here, n is 4. So those first entries in, the Cn1s, are all equal to n. Anyway, there it is. If you're into mathematics, this is beyond this course. You wouldn't be asked to prove any of these rules in this course. Let's come down, because we've actually tooled up quite well here now, and we can do some problems. So if we have a question like this, you would not like to do that from first principles, would you? Putting an animal like that into f of x plus h? No. So can we do it with our new rules? Here we are, 5x cubed. So the 5 stays there, it's a constant. What is derivative of x cubed? 3x squared. Remember the rule. X to the n goes to nx n minus 1. So then the original power goes in front to the 1 less power. So we got 6 lots of x squared, so we've got 6 lots of its derivative, which is 2x. Neg 3x, 3x is 3x to the 1. So it's 1 by neg 3, x to the naught, which is just 1. Derivative of a constant is 0. So then we'll put it all together. What about these here? These terms are a bit problematic, because you must get them in the form that you can use your tool. That's the x to the n rule. So 4 on x is 4x to the neg 1. And 3 on x cubed, 3x to the neg 3. You can see why you need so many tools in mathematics. Here we're using index laws to help us with calculus. So here then, derivative of x is just 1, what we did before, and you've got 7 lots of it. We've got neg 4 lots of the next one. Derivative of x to the neg 1 is neg 1 out the front, x to the 1 less power. Neg 1 take 1 is neg 2. Then you've got 3 lots of, now this power, neg 3 goes out the front, x to the 1 less power. Neg 3 take 1 is neg 4. So, just go back up here now, while you're with me over here. What are you doing? You put the power out the front and raise x to the 1 less power. So if that power of x is negative, 1 less is a more negative number. So just watch that little trick. Now, I've gone too far there, so just come back and have a look. We've dropped right down here. I don't know why I just did that, but here we go. So what I want you to do is those problems there, and I think you should do all of them. You can see down the bottom here, in these you should divide through by the denominator first and make up single powers of x, and then use the x to the n rule. We might pause the presentation now, have a go. I'm just going to show you the answers here down below, so you can come down there at any time and check your answers. Alright, so going back, and we'll just leave it maybe there, so you can have a go at those problems and check it out. Just remember, these last 4, you need to do something to the function first. You need to divide through by the x or the x squared to get single powers. Because remember, at this stage you've only got that goes to that. That's the only real tool that you've got at the moment. Okay, well, let's come down now and have a look at another example. Find the slope function of that, and hence the slope of the tangent. Well, that's the same thing, isn't it? Remember the trichotomy. This is very important when you're talking about the derivative. Okay, the derivative, it's the slope of the tangent. Okay, so that's important, but it's also the instantaneous rate of change. So there are 3 things all linked there. They're the same thing. So here we want the slope of the tangent, so it means we need the derivative. So let's do it. Derivative of x squared is 2x. And then neg 4x, well, we needed to think of that first as neg 4x to the neg 1. Because then we have neg 4 lots of, the derivative of this is neg 1 x to the 1 less power, neg 2. And then because you want to substitute in and find the actual slope of the tangent at x is 2, it's best to think of x to the neg 2 as 1 over x squared. And then subbing in, you've got that. A lot easier than first principles. Okay, so let's have a look at your problems here. There are some problems for you using just that rule, so the answers are right there handy by. So you can work through those. Can you see what we're doing? We're building up our ability to apply calculus to slopes of tangents, instantaneous rates of change by using rules on functions. Okay, so let's come down a bit now. And this example here. So we're just getting into more applications of the x to the n rule. So find the slope function, or the derivative, or find the instantaneous rate of change function, all those. So let's look at this first one, needs some work. 3 root x you'll call 3x to the half. And 2 on x, 2x to the neg 1. Why? Because your only tool that you've got at the moment is that one. Okay, and then you do it to it. So 3 lots of the function, 3 lots of the derivative. And then it's a half x to the 1 less power. Half take a half is neg 1, neg a half there, sorry. And you've got 2 here, x to the neg 1, so it's neg 1 the power by x to the 1 less power. Neg 1 take 1 is neg 2. Just remember over here, you reduce the original power by 1. So if it's a negative and it's neg 1, it becomes neg 2. If it's x to the neg 2, it'll become to the neg 3. And then, of course, combining your terms up here, it's important, I think, if you're going to evaluate, and you don't do this if they don't ask you to, but if you want the slope of the tangent and you want to stick numbers in it, it's probably better to have this line, where you don't have x to the neg half, you interpret that as negative is 1 over, a half power is root x. So x to the neg 2, just remembering this, is 1 over x squared. Because we want to actually use this derivative to find slopes of tangents later on. So we need to put it into a more usable form. Okay, well, let's look at the last one. We actually have to work on 4 on root x, because 1-ons are negative powers, and root x is a half. So it's 4x to the neg half. Then we do the first one, that's alright, 2x. And then we've got 4 lots of this function. So we've got 4 lots of its derivative. And then neg a half, x to the, did you get that? Neg 3 over 2. N was neg a half. N take 1 would be that, which is neg 3 over 2. So just watch this over here. Reduce the original power by 1 and watch your work with negative signs. So you've got this creature here, a more usable form. First of all, negative means 1 over. 1 over x to the 3 over 2. But here, as they're explaining it, 1 over x to the 3 over 2 could be thought of as x root x. Just to make it easier to substitute in, perhaps, if you were going on to apply it to actually finding a slope of a tangent. Okay, let's come down here. Some problems for you. Same thing. Don't forget, you only have this rule. X to the n must be done first. You must convert to a power first of all, so that you can then find the derivative using the x to the n rule. Alright, you can pause it and have a go. I'm going to keep going now. Can you see what we're doing? We're attacking harder and harder looking functions. Okay, so here's a function, and we want its derivative and interpret its meaning. So its derivative is fairly easy, because it's just 3 lots of 2x or 6x, and derivative of neg 4x is just neg 4 from our x to the n rule. So here's our interpretation. The slope function for which the slope at any point can be found is 6x take 4, or the instantaneous rate of change. There is a trichotomy. The derivative means you have a function which will find the slope of the tangent or the instantaneous rate of change. So be flexible in that. So I'll get you to have a look at this question, interpret its meaning. And And all of these, you might like to look at this one, because this is our Newtonian approach to differential calculus, the rate of change of distance with time. So what ds by dt is the derivative, the rate of change of distance with time. So you might like to give a good interpretation of that. All right, so down here are the answers. So go back, have a go, and then come down and see what interpretation you've got and compare it to the answers there. All right, so moving on. You would realise we're talking about very simple functions at the moment. So what about the more complicated ones? Okay, well, the more complicated ones are where a function has been done to a function already. Well, function's been done to another function. So this is the square root of a function already living in there. And this is the reciprocal of a function. So they're composites. As in a composition, composing something. You're putting it together. So we are actually composing two functions here. So y might be u to the fourth, but u is x squared plus 3x. So you're not doing the fourth power on x, you're doing it on a function already there. So here we could talk about this one as the root of u, but u is 2 take 3x. And here this is 1 on u, because u is already a function. So we're trying to actually analyse more complex functions, because we want to find the derivative of these as well. So to understand the function, let's have a look down here. F of g of x, if you do f, here it is, what does f do? It raises the variable to the fourth. So if you do f on g, g's been done, and if you do f on it, you're going to raise that to the fourth, not x, because you're doing it on the result or the range values of g. Let's come down and do some practice in understanding here. So these questions are designed to just get you to analyse how functions are put together. So f of g of x means f done on g. So let's go up here and do some of these. If f of x is 3x squared and g of x is this, then f of g of x means do g first and put it in the x hole in f. So it becomes 3 times, not x squared, but that. Okay, so this is notational. What does f of g of x mean? It means f has to operate not on x anymore, but on g. So now, in this example, f is the square root. So instead of finding f of x, you're finding f of g, and g has already given you 3 take x squared. So it's the root of 3 take x squared. So what we want you to do now is to do f here on, not on x, but on g. So g's got to replace x in all the spots in the function f. Okay, have a go at those, and also there's one down the bottom here in question 2. Try to unpack. Can you go backwards and say what function was done first, and then we put it into another one? Have a go at those, and we'll just go down and have a look. So there are your answers, just to scroll on and have a look and then go back afterwards. Okay, so 2 questions there. Probably, we'll just go back up here. 2 questions there, probably worth doing all of them, I think. We'll just come there. Probably worth doing all of them. All right, I'm going to move on, so when you're ready you can come along with me. Let's have a look at what we've been doing. And I think you can see, if we look at this, where you have a function done on something that's already a function in x, you've got to do the power first and then multiply by the derivative inside there. So here what they're saying is, if you have this function, then you could expand it like that and do every term one after the other. Is there a quick way? So that's that. Is there a quick way rather than expanding it like this? Is there a quick way of getting to that endpoint? Can you see it? So here we're looking at this expanded and then we're getting its derivative. Is there a way of getting straight to there? And that's what this is up here. We can say, I could just do the power part of this function. Let's do it over here. 2x plus 1 cubed. Rather than multiply it all out, let's do the derivative, dy by dx. Let's do this part first. So the power, 3 by 2x plus 1 to the 2, multiplied by the derivative of what's in there. So the rule here is, of course, saying that I'm looking at this as u and just doing the power part, then I'm going to multiply by the derivative of u. So it's splitting functions up so that you can do the derivative in parts without doing all this expansion up here. We're trying to avoid expanding it and just taking, there's the function, and saying I'll find the derivative of the cube with respect to u. So this whole thing here is dy by du, and then I'll multiply by the derivative of u with respect to x. I'm thinking of this as a single variable there, and then multiplying by how it's varying with x. Let's have a look at their proof of this. So here's the line. If you have y is some function in something that's already a function in x, then get the derivative of y and then multiply by derivative of u with respect to x. So if you had something like this, you would have n out the front, so we're going to do that power, the power function, dy by du, holding what's inside there constant to the one less power. So we're thinking about then this as the variable, or u, and we're just doing the n part, and then we multiply by the derivative of what's in the bracket. So there's a little proof here, and I think this is important to say, well, why is that the case? Well, if we said we're trying to find the rate of change of y with respect to x, then what we could do is let's look at how u is changing with respect to f of x. Okay, so here as we come along here, and that actually is our line here, dy by du. So we actually have a little mistake here, because we should be looking at dy by du and then du by dx. I think we've got them around the wrong way here. So here, dy by du, we look at that, and that's this one here, and dy by dx is eventually then times du by dx. So this should be actually x in here. Dy by du, so we're looking at how we're going up. If we plotted y against u, we're getting that rate of change, so that's that there. Okay, dy by du, and then du by dx. This should be x over here, and we're looking at du by dx. And when you multiply those together, you are talking about fractions. We haven't brought in limits yet. So this one first, and then that one. So dy by du, so mess this up in the book a little bit here. Okay, so then we could do some limits. So the limit as delta x tends to naught of delta y and delta x is the definition of the derivative, and then it's the limit as delta u tends to naught of this one, delta y and delta u, times the limit as delta x tends to naught of delta u on delta x. So we just forget about that there. Okay, so what that means is the overall derivative is a product of the derivative of the parts. Okay, So notice that we've used a much better notation than f of x plus h take f of x. This is neater than doing all of this in the top line, just to symbolise what we're doing in general for a function. So the important take-home message there is to multiply by the two derivatives there. One of the first function and then with respect to the other, and then with the second function. Let's look at an example. So if we go to this one here, can you see we have two functions, that one and this one? So we're going to now, I don't think you need to put all the u's in. So we can go straight here. Well, if you do u, you can say u to the fourth and u is that. So you then put the rule. So you've got, if this is u, it's 4u cubed times the derivative in brackets. You can do this more simply. Simply say dy by dx is, let's do the power part first. It's 4 by x squared take 2x cubed, multiply by the derivative in the brackets, 2x take 2. So you're doing here the derivative of the fourth power with respect to u, dy by du. You treat this as a variable and don't do anything, and then you do the derivative to that variable. So if we look at the next one here, you've got 4 by 1 take 2x to the neg a half. So you could call u this function in here, and you've got that. So we've got 4 lots of neg a half u to the 1 less power, and then we need to multiply by the derivative of u, which is neg 2. We've got that. I would again go across here and say, well, if I had y equals 4 by 1 take 2x to the neg a half, leaving out the u's, just thinking of them in your mind, I have two functions. First of all, let's do this. So it's 4 times neg a half 1 take 2x to the neg 3 over 2. And then I've got to multiply by the derivative of what's in the brackets, which is neg 2. So we'll come to the same thing. I think it's a little bit easier to think of it this way, where you're doing the power function and then multiplying by the derivative of that other function. Alright, so we're getting messed up here with this. I'm going to go back. Okay, we've got to go way back. It's skipping badly here. Okay, so these functions, it's important to do them as two parts. You can let u be something if you wish, or just go straight in and look at trying to identify the two functions. Obviously, all of these you must change to the power, must have a power form first. Okay, so they all require that. So x squared take 3 in the bottom line there would be x squared take 3 to the neg 1, and go on from there. Alright, well, the answers are there. You need to pause the presentation and have a go. I'm going to go on now. We'll just go down here and have a look at some more examples of the same thing. We'll just bring these answers up. So you're trying to find the slope function again. So again, you must have the function in a form suitable to starting with, for starting. And so, you know, these here should be changed to powers of a half. You might like to also change these in here. This is over 3x take x squared. So the use of the neg 1 power would be useful. And here, the neg 2 power. So have a look at those, have a go. And same idea, identify the two functions, do the first one, and then multiply by the derivative of what's in the brackets. Okay, so you might like to pause the presentation and have a go. let's go down and take all these individually. So here, more of the same thing now. So all of these need to be looked at in the first instance as a functional composite functions. Identify the two functions. So you might actually have to change things like the cube root of 1 take 2x to 1 take 2x to the 1/3. And can you notice they're asking you to actually evaluate the slope of the tangent. So you find the derivative expression and then you substitute the x value in at the point where you want the actual slope of the tangent. And here the answer's down here. So have a go at those. Alright, another one now. Just a more theoretical question. If y equals x cubed and x equals y to the 1/3, find dy by dx and dx by dy. So they're interchanging the variable name now. So what you were doing with x before, you now do with y, if you like. You dx by dy. So think through that a little bit and have a look then at the answer. Alright, let's go down. Product and quotient rules. You would obviously know that we haven't actually done any functions that are consisting of two functions multiplied. We know when two functions are added, it's the derivative of the first plus the derivative of the second. When two functions are multiplied, is it the derivative of the first by the derivative of the second? Is it that easy? And the answer is, of course, no, it's not. And we're going to have a look at that now, because it is actually the derivative of the first function by the second unchanged plus the first unchanged by the derivative of the second of the two functions in the product. Well, it's not in the course for us to actually prove that, but why don't we have a go and have a look at it? So let's start with f of x equals u of x times v of x. So then, starting with our definition always, f dash x is a limit as h tends to 0 of fx plus h, take f of x on h. Okay, this is the limit then as h tends to 0 of u of x plus h times v of x plus h, take u of x by v of x. You can see this is going to be complicated, this product. Okay, so then it's a limit as h tends to 0. Let's try to construct a derivative in here. So u of x plus h by v of x plus h. If we took away u of x by v of x plus h, we would be constructing a term with a common factor, and the other one would be the derivative, u of x plus h, take u of x. So that's a little trick. Now we can't just subtract that. Let's add it on to keep the balance of that equation. So there it's balanced out, and then we've got this term on the end. So this is a little trick that is worthwhile remembering if you're trying to prove this. So we're going to construct some derivatives now. Let's take out v of x plus h out the front of this first two terms. It's u of x plus h, take u of x. So there it is. There is our common factor term. And you might start to see a pattern here. Now in the second lot, what have we got? Have we got a common factor term? Yes, u of x. So it's u of x outside of v of x plus h, take v of x. Nice little algebraic manipulation happening here. Okay. Then what are we going to do? Limit as h tends to 0 of, let's package this first group up. It's v of x plus h times u of x plus h, take u of x on h. So that's packaging that up, plus u of x by v of x plus h, take v of x over h, packaging that up. Can you see it now? Now this is the limit as h tends to naught of the separate functions. So it's v of x plus h times u of x plus h, take u of x on h, plus the limit as h tends to naught of this thing, v of x plus h, take v of x on h. Let's look at the limit of this first term. Now, as h tends to naught, in here, v of x plus h will tend to just v of x, h is tending to naught, times, the limit of that, that's the definition of the derivative, isn't it? U dashed x, plus, same thing here, as h tends to naught, u of x just tends to u of x, hasn't got h in it, not affected. And the limit as h tends to naught of that, by definition, is v dashed x. So, let's put the u term in front, because that's how we always remember it. So, it's u dashed x, v of x, plus u of x, v dashed x. And there's our rule, as required, if you like, if we were asked to prove that. So we've done well there. Now that's not in the course, just something, if you're interested in mathematics, something that you might appreciate. Alright, let's go down and see if we can do some problems. So here are some problems involving products. There's a function and there's another one. So first of all, you might think of the first function as x to the half, second function is that. You don't have to actually write the rule every time, but it's the derivative of x to the half, which is a half x to the negative half, by the second function unchanged. And then the first one is left unchanged, and this is the derivative of this one up here, 2x plus 3 all squared. So remember, in doing this one, it's 3 by 2x plus 1 to the 2 multiplied by that 2 in there. Excuse me, function of function. So that's how you get the 6 in there. And then you could simplify it. Generally in tests, when there are derivatives of larger functions, they say do not simplify your answer. Let's have a look at this product. There are the two terms. So, derivative of x squared is 2x. Second one unchanged, plus first one unchanged by the derivative of the second, which is all of that. Let's just check that, because x squared take 2x to the fourth is a function of a function. That will lead you to 4, do the power part first, to the 3, and then you must multiply by the derivative of your other function, 2x take 2, using a bracket there. Alright, are you ready to have a go? So let's have a look at these. In each of these cases, of course, it's important to use things like a half power for square roots and things like that. Identify your two functions, and it's the derivative of the first by the second unchanged plus the first unchanged by the derivative of the second. I wouldn't put in all the u's and v's, it's going to take too long. Find the derivative, find the slope of the tangent, means the same thing. You're going to find the derivative and then substitute the numbers in to evaluate it. And here they ask you to show that you're going to get that at the end. So a little bit of algebra there, go through it in the same way, calling this one x to the half, and then trying to simplify it at the end. Let's come down and look at the answers down here. Alright, so there are our answers to that little batch of questions. Alright, so go back up now and have a go at those. We'll just put them there and go back down and have a look at the answers in a minute. Alright, well, I'm going to go on now. So let's have a look at the quotient rule. If two functions are divided, so there are two functions divided, there's another two functions, so you're talking about a u of x divided by a v of x, and we're going to use the product rule to have a look at this. So I don't know, there's the book's definition. They've multiplied across by that q of x and then done a derivative on that, saying that if this is a product, then u dashed x is q, first one, a derivative of the first one by the second unchanged, the first one unchanged by a derivative of the second, and then grouping u dashed x over here with the neg q to get q dashed, and then eventually rearranging it, so neg u dashed x. We've done a couple of rearrangements here, a change of sign, and so getting a q dashed x v of x is going to be putting q of x back in there and then coming up with that. There is another way of doing that. I might show you over here. Q of x can be thought of as u of x by v of x to the neg 1. I think this is easier. And then the derivative is the derivative of this one by the other one unchanged, plus this one, first one unchanged, by the derivative of the second, which is neg 2 times v dash x by the composite or function rule or chain rule. So here then, what have we got? We've got u dashed x over v of x, and here it's going to be a take u of x over v of x, so neg 2, times, we've got it here, v dashed x, and then getting them over a common denominator, v of x all squared. This has to be multiplied by another v of x to get it over that denominator, so we've got that. Okay, so that's another way. That's a complicated rule there. How do you read it? You do the derivative of the first, the top line, by the bottom line unchanged, minus top line unchanged by derivative of the bottom line, all over bottom line squared. Okay, so it's important to sort of put that in words so you can see what's going on there, rather than sort of blindly substituting in. All right, so let's go on now. And there's a formal statement from Hayes, and Harris of those. This is the one that most people think of. On the formula sheet in an exam it looks different again, so you might have a look at that. Different notations, f of x and g of x are sometimes used, but it's important to put it into words. Derivative of the top function, if you like, times bottom function unchanged minus top unchanged by derivative of the bottom all over the bottom function squared. No matter what symbols you use, it's important to have that interpretation. Okay, let's come down a bit now. We're building up towards being able to do quotient functions now. Alright, so with the quotient functions here, it's important to use the rule which says, okay, first of all, in this first one, it's the derivative of the top line, which is 3, by the bottom line unchanged, minus the top line unchanged by the derivative of the bottom line. And then simplify, all over the bottom line squared. So let's go down and look at this one here. the top line, the derivative of that, half x to neg a half, bottom line stays the same. Minus top line stays the same, derivative of the bottom line here is 2 by, let's do it over here so you can see it, the book hasn't spelled it out. This becomes 2 by 1 take 2x to the 1 times the derivative of the function. Here it's a function of a function, so it's neg 4 1 take 2x. So that composite function of a function, or chain rule, there you get a chain of derivatives here. Don't forget that. And then this is how you'd usually leave it in tests. They say don't simplify your answer, but you can multiply this out here, getting a positive, and then trying to simplify the square roots to get a simpler form. Okay, but we're not going to worry too much about this simplification here. You can have a look at it, but at the moment we'll want to perfect this quotient rule application. Okay, so coming down here, we'll just give you the answers here in a minute. It's important to remember the rule as derivative of the top by the bottom unchanged, minus top unchanged by derivative of the bottom all over the bottom squared. So have a go at those. Maybe just put this down here. Oops, there we go. We're doing this again now. So here we go. Have a go, and I just peek down here. I've actually put this time, because it's more complicated, fully worked solutions from Hayes and Harris. So you can have a look at those as you do them. So just go back up, and there are the problems. Pause it, go back and have a look at your answers and check it out. Okay, well, let's go on then and have a look at some applications. Find the slope of the tangent to these. So it's the same thing. It's a quotient rule, but then you're going to substitute numbers in to the derivative to actually find the value of the slope of the tangent. These are the same thing here, using the quotient rule with a bit of care. Don't forget, if it's root x, to do that, get the derivative of the top line, you've got to call it x to the half. Okay, so I'll just flash these answers for you. Got the fully worked solutions there now. Let's just see if we can get those there. Okay, so there are 2A through D. We'll pause that, and then question 3. Come down here a bit. Alright, so coming there, having a look at those fully worked solutions. Alright, okay, well, you might go back and have a look at those problems and see what you think. And then join me as I go on now to have a look at some of the final rules. Okay, so what are we doing? Remember, we're trying to tool up to be able to do the derivative and therefore find the slope of the tangent or the instantaneous rate of change for any type of function. Well, we're almost there, but look at this creature here. This is called an implicit relation. Right? It's not actually a function when you plot it, and we can't write it explicitly, y equals. That's an explicit statement, as y equals some function in x, something like this, whatever that might be. That's an explicit statement, and we just dy by dx it, don't we? We differentiate it using our rules. Now you can't do that. There's too many y's here. You actually can't separate the y's in this function to get a y equals. So what do you think we might do with it? Let's go down and have a look. Let's have a look at x squared plus y squared equals 4 and use our brain on this. Let's do the rate of change of both sides, one term after the other. So we'll find the rate of change of x squared plus the rate of change of y squared, the rate of change of 4. We said we could do that with the sum of functions. So derivative of x squared is 2x. Derivative of y squared, oh, we better bring that over here. Well, that's a function of a function. It's a power function of y. So let's do the power first. That's 2y. And then we generally multiply in brackets by the derivative of that. We don't know what y is explicitly in terms of x, so we're going to put a symbol there. So we're using the function of a function or chain rule with the realisation that we do the power, get 2y, and normally, usually, we would multiply by the derivative of y with respect to x. But we don't know what y is. It's some function in x, so we use a symbol for it. And then the derivative of 4 is a constant. And after all that, so here's their explanation down here of y derivative of y squared is 2y dy by dx. But after all that, if we rearrange this line, we would find that dy by dx is neg x over y. Do you want to check that? 2x plus 2y dy by dx equals 0 implies 2y dy by dx equals neg 2x, which implies that dy by dx is neg 2x over 2y, or neg x over y. Okay, so you're going to have y's involved because we didn't ever have y as an explicit function in x. Let's have a look at what we can do with that type of situation. So here's a few here. So here we're just practicing. Derivative of y cubed, what will you do? Well, it's 3y squared to do the power. But we don't know what hidden function is in y, what y is as a hidden function or implied function in x. So we put a symbol for it. Okay. So if we're talking about how y cubed is changing with respect to x, we're implied that y is some function in x in that hole there. But we don't know what it is. So what about 1 on y? That's the derivative of y to the neg 1. So let's do this power, neg y to the neg 2. So we're doing the power part. We don't know what is hidden in there in x land. So we will say we should multiply by the rate of change of that y with respect to x. And the last one is interesting, getting more onto the level for this course. You're going to do a product rule. So it's a derivative of x by y squared unchanged, plus x unchanged by the derivative of y squared, 2y, and then multiply by the derivative of that implied function in y. Okay, so here are some problems for you. These are actually the answers here, right handy by, so you can have a go. Don't forget, in y land there's a hidden function or implied function in x in there, and so you need to accommodate that. Alright, so pause it there, have a go, you're going well. This is a big unit trying to get through all the functions that we might come across so that we can find the slope of their tangent or the instantaneous rate of change. Right, another example, Hayes, Hayes and Harris here now, and this is the same sort of idea. As we go here, derivative of x squared is 2x. Oops. Here we are, we've put it there. Derivative of x squared is 2x. And now derivative of y cubed, do the cube function, 3y squared. Then dy by dx is a symbol representing the rate of change of that hidden function in y. We don't know what it is in there, how many x's there are in there, and the derivative of 8 is a constant, so we can rearrange it. Okay, so we're coming up to the level that would be required in tests and exams here. So let's have a look at this function. Derivative of the first term is 1. Derivative of this is a product. So the derivative of the first term is 2x by the second unchanged. Plus first term unchanged. Derivative of this one, don't know. Got to put a symbol. Because again, we don't know explicitly what function in x is hidden in there. And then the derivative of y cubed is 3y squared. And that's doing the power function with respect to y as a variable. Now there's a hidden function in y there, so we want to multiply by its rate of change. So then you could actually collect up all the dy by dx's. They haven't shown that step here. I would have said put 1 plus 2xy plus dy by dx x squared plus 3y squared equals 0 as an intermediate step. So we're actually taking dy by dx as a common factor out of those two terms. And then we'll put that over there and get neg 1 take to xy and simplify. Okay, have a look. There are some problems with the answers alongside here, making it easier to check. I would tend to do all of these problems and get skillful at doing this sort of differentiation. Implicit differentiation, when it isn't set up, the function is not set up as a y equals. You can see y is dependent upon x because they're all in there together, but it's not set up that way. So let's just come back. That's skipped up there. Okay, so you're there, and what I'd like you to do is have a go at those problems and move on. I'll catch you as I go on here. Alright, so they're all along the same lines. Find the slope of the tangent. Remember the trichotomy. If you're getting the derivative, then you're getting the slope of the tangent, or synonymous with that, instantaneous rate of change. Okay, so any of those. So here we want the slope of the tangent when x is 2. So I've got to get the derivative of this. Derivative of x squared is 2x. Derivative of y cubed, do the cube part, 3y squared by the hidden derivative of y. Here with respect to x, and the derivative of a constant is 0. Rearrange. Then when x is 2, you first of all got to work out y, because can you see with implicit differentiation you need both x and y values at the point to find the slope of the tangent. So therefore we've got neg 4 over 3. So gradually building up here. Question 3 there. Very good. Have a go. Answers are over here. Right, going to move on. So let's have a look at actually finding the equation of some tangents and normals. Just remembering what we're going to do. Newton was unhappy with average rates of change. He brought that chord along to tangency. So the average rate of change was the slope of the chord. Average rate of change equals slope of the chord. The instantaneous rate of change, which is what he wanted for his motion problems, equals the slope of the tangent. Okay, so remember what we're trying to do is to find f dash x and evaluate it at a. Stick a in there, and that's going to give us the slope of the tangent. Just a bit of a review of what we're doing. And then of course we might want the perpendicular to the curve, and that's called the normal, so that's at 90 degrees. And of course there's something to remember there. The normal perpendicular to another line has a product of its slopes equal to neg 1 between the lines, so m2 is minus the reciprocal of m1. They are the definitions for the slopes of lines at 90 degrees. And the normal is defined as a line perpendicular to the curve and to the tangent, therefore at a particular point. So remember that. Alright, so let's go down and see if we can use our derivative to actually find some tangents and stuff, equations of tangents. Well, I think what we're going to have to do is go back and revise that. I don't know whether you remember how to find the equations of lines. Okay, equations of lines. I think because they're both straight lines, aren't they? Tangents and normals. I think there are two ways that most people have learnt it. Okay, the first one is y equals mx plus c. Okay, and for example, let's say f, let's say f dashed, let's go over here, f dashed of 2 was equal to value 3. So that meant you had a slope of 3. So you put in 3x plus c. And then what would you do? Well, you need to have a point. So you'd substitute the point in. Let's say the point was 2, 5. And then put 5 equals 3 times 2 plus c. Do you remember this? It's a long way, fairly long way of getting the equation. So y equals 3x, take 1. That idea where you have to have the slope, you put it in place of m, and then you substitute a point. The other way is to say so this is based on slope and intercept. The other way is to say, well, if I have a point 2, 5 on the line, if I want a general equation, I'll create a general slope. Y, take the y coordinate of the point on the line, x, take the x coordinate, equals the slope. And then if I find the slope using calculus, which is what we've been doing, if f dash 2, for example, is 3, well, we'll put 3 there, and then we multiply both sides by x take 2, and we get 3x take 6, or y equals 3x, adding 5, 3x take 1. Get the same answer. Actually, in this course, because we might have fractions for the slope, this is an easier way of doing it by and large. Okay, so you might look at this. However, choose whichever way you want to do it, and just check your answers as we go. Right, let's go down and start using our derivatives like that. So here, find the equation of the tangent, not just the slope. So the first thing we need to do, when x is 1, let's find what the point is. So it's the point 1, 2. Do you remember that? When x is 1, stick it back in there. 1 squared plus 1 is 2. So you can find the y value of the point by substituting the x value in the original function. We'll step back up here. Now we need to know the slope. So the slope is the derivative, which is 2x. At the point where x is 1, we can evaluate it, and then we go into the equation idea. Y take the y coordinate of a known point on the line, over x take the x coordinate, equals the slope, and then multiplying it out. So can you see, what do we need? We need a point, and we need the slope. So when you're working with equations of tangents and normals, that's all you have to think about. Have we got the required information? Okay, let's go and do another one. Here's another one. Find the equation of the normal this time at x is 4. So first of all, when x is 4, stick it in here to find out what y is. So we've got the point 4, 4 that's on the curve. So picturing it over here. Now let's get the derivative, because that's the slope of the tangent. So first of all, we've got to change this to 8x to the neg half, the x to the n rule, and then differentiating it, or getting the derivative. Got 8, and then it's neg half, so let's do this in stages. So this then goes to 8 times neg half x to the neg 3 over 2, which gives us neg 4, x to the neg 3 over 2. And therefore we need to evaluate that when x is 4. And 4 to the neg 3 over 2, better watch that. That means 1 over, the half power means root, so it's that. Negative power means 1 over, and that fractional part means the square root, so you've got neg a half. So now we've got a point, and oh, hang on, we want the normal, so we've changed neg a half to minus reciprocal, which is 2 over 1. So we now have y take 4, y take the y coordinate point on the line, x take the x coordinate, equals 2. Multiplying across, we have 2x take 8, and so on. All right, come and practice. Just keep your wits about you. Are you doing equations of tangents, so you keep the slope equal to the value of the derivative at the point, or normals, you've got to use minus 1 over. So you will evaluate the slope of the tangent at that point, the derivative. When you've got a number, then put neg 1 over it. Okay, so let's have a look then at those, and down here we've got the answers there, the fully worked answers. So that's up to end of question 1 and question 2. I put those there because these are a bit more work in some of these, and want to make sure you can follow it through. So you can pause that when you're ready, and that's just come down here. This is question 1. Let's just make it easier to capture that. All right, so there are the 2 questions. All right, have a go. We're coming to the end. We've almost got all the tools we want and are starting to apply them. Okay, so let's go on now. So we're getting some variations in questions now. Find the equations of horizontal tangents. Oh, horizontal, we better find the value of the derivative. And if it's horizontal, we want to know the points where the slope is 0. Horizontal tangents, these here. So we need to actually find out where those slopes are 0. So we'll put the derivative equal to 0 and get 2x values. Okay, so here, what do we know? We needed to know generally a point and the slope. Hey, hang on, they gave us the slope and we had to backtrack to find the point. So we found where the derivative was 0. At those 2 x values, substitute them in and get the 2 points, and then we can find equations at those 2 points. You need for an equation a slope and a point. But this is going to be horizontal, so it's easy for the equation. It's going to be y equals a constant in those 2 cases. So it's going to be y equals neg 14 and 18. So the equation this time is quite simple because we know it's horizontal and it has this form, and we've got the y value of a point on it. Let's do some. So here are some here which have curly pieces, horizontal tangents. Find k at the point where x equals 2 if it's got a slope 4. So we're given the slope and we've got to go back and find something about a point. So there's some little tricks in these. This one is parallel to a tangent at another point. Well, we better go and find what the slope of the tangent is at that point so we can use it. Here we are, we've got a and b are 2 constants. You'll need 2 pieces of information to find the values of a and b. Can you find perhaps a derivative piece of information and a point on the line type piece of information? Because you do know that that is a tangent, and so it shares a point of tangency with the curve. Okay, you might pause that and have a go. Down here are the fully worked solutions, again because there's a fair bit of work in those. That's question 3. Go back and look at those later. And question 4, part A and B. Okay, so might have a look at doing those problems and going ahead and just having a look at the answers. All right, we're going to finish off now very shortly, and let's have a look at our last little bit. Okay. we want to find an equation of a tangent here at a particular point, and we're getting some messier looking functions. So the same thing holds. So if you are trying to do that, you've got x is 3, put it in the function, get the y value, so you've got the point, get the function with a half instead of the root, then it's a half to the neg a half, leaving this unchanged, function rule, or chain rule, multiplied by the derivative. So you do the power, leave this unchanged, and multiply by its derivative. Then we've got to evaluate it at the point, which was that x is 3. It gets messy because you've got these neg a half. Neg a half means negative 1 over. Half power is the root. So here this form is easier for finding the equation of a line now, because you've got this fraction. So it's y take the y coordinate point on the line, over x take the x coordinate, and then we're going to multiply by 2, and x take 3, so effectively it becomes 2y take 2, if you like, and 3x take 3, because the common denominator cancels out those other 2. So here are some problems for you down here. Question 5 and 6. So not bad, just watch out for the normals, because you've got to do something with the slope, don't you? Mine is the reciprocal of the slope. So have a go. Down the bottom here are the fully worked solutions again. I think, what have we got there? Question 5. Just check those out, and I'll just go back so a bit. Question 5 and 6 is there, I think. Let's have a look. Maybe 6 isn't there. No, I think it should show that. So 6 is not there. Yes, it is, right down the bottom. Okay. So have a go. And I'm going to move on now to equation of a normal, and this time can you see what we're doing? Just making the function more complicated. So when x is 1, substitute it in, you get the point neg 2, so the point is 1 neg 2 you're using. Look at this, the quotient rule. Derivative of the first term, second term unchanged, minus first term or top term unchanged by derivative of the bottom, over the bottom squared. So it's all a bit messy. Sub in x is 1 for your point. So the same thing, but here we're working with a normal, so the slope becomes m equals minus 1 over 2, because it's a normal. Don't forget to change that. And then the usual way, y take the y coordinate point on the line, over x take the x coordinate, multiplying across, because you're effectively multiplying by the common denominator, 2 outside of x take 1, and we come up with an equation. So have a go at some quotients and some harder ones down here. There are 4 of them. You might pause the presentation, have a look. I'm going to just flash the answers down here. Fully worked solutions, so you don't get caught. That one there. Okay. So have a go at that and see what you think. All right, we'll go on now and just check your answers as you go. All right. Coming to some interesting parts here. Obviously we're going through all the functions that we did before, finding the equation of the tangent. Here we know the point, so now the differentiation of this, 2x, this is a product, so put the negative out the front. Derivative of the first term is neg 3 by the second term unchanged, plus the first term unchanged by the derivative of the second, dy by dx. Derivative of y squared, do the squared part first, 2y dy by dx. So we need to collect up now, and we can substitute in the point, neg 1, 4. Oh, they've got 1, 4 up there. Anyway, neg 1, 4. I think that's a misprint. This should be positive. So substituting in there is 2, working it all out, collecting up the dy by dx's, and you get a slope of 2. So then you have your standard approach, slope of 2, y take the y coordinate, or x take the x coordinate, etc. So what are we doing? We're going through all the functions finding slopes of tangents, even though the function is complicated, and this is probably the most complicated ones because they're implicit functions. All right, study that. You might rewind it and check it. Have a go now at these down here, question 8 and 9. So you can pause that. I'll just go down and show you these answers here. So I think that's 8 there, so you can pause that and see what's going on. And then 9. Okay, so have a look at 9. 9's an implicit one, so a fair bit of work in that one. Alright, so going on to finish off, here's another one where you want to find where the tangent to the curve meets the curve again. So go through the same process. You have a function and you have a point, get the derivative, find the slope. Now we've got the equation as before, usual method. Now, this is important. Where does the line, which is a tangent, meet the curve? You put the y from the curve equal to the y from the tangent. You get this thing here. And then where a graph is a tangent to a curve, and you're looking at points of intersection, you'll get a repeated 0 here. Okay, a repeated 0. So what that means is that x is equal to 1 where there's a tangent. X take 1 squared would be a factor. So you know the first term has to be x to get x cubed in our equation, and the n number is 2. When you square this out, it'll be plus 1, so you can sort of backtrack and get 2. Or you could do it on your calculator. You could solve this on your calculator. This is actually not part of the course. You could solve that on your calculator and find that they intersect at 1 or -2. 1, of course, was the point of tangency, so the other one, -2, is the point where they meet the curve again. So putting in -2 into the function, you can find that the other point is -8. So we're looking at this sort of picture. Tangency, and where does it meet it again? So you've got to find the equation, and then to meet, you're putting the two y's equal and solving the equation. So there's some curly pieces in these as well. So there we are, there's 4 of them there. So, and there's our 4 answers. Hope we don't quite fit on there. So we'll just go down a bit there. I want you to go down and have a look at those, but at the moment, having a go just at those questions there. You can pause that, and then going on. Alright, so you're getting quite sophisticated here in what you can do. Okay, so we're just going to do a little bit more. Equations of tangents to a curve from a point. Oh, that's different. Usually we know the point. So here we are drawing a tangent to the curve and we don't know where it lands. So here's the secret. Let the point at which it lands be a, and then sub a into the function to get a squared. Okay, so now you get the derivative 2x evaluated in A land. This is quite different because you don't know the point where it's landing. So this is an important little algebraic trick. So now you say at that point, I've got my point, the slope is that, and you make up the whole equation like before. Y take a squared over x take a equals 2a. The book's left this out. And then for y take a squared equals 2ax take 2a squared. Okay. And they're doing things there. So here, our equation is this thing here. and you'd put it as y equals 2ax, take a squared, put that one on the other side, so it'd be like that. So I would do it that way, going back to the usual setup, y minus the y coordinate of a known point on the line, x minus the x coordinate. And then you can sub in 2, 3, because you know it heads off from that unknown point to 2, 3, and you can find 2 possible a values. So therefore you've got 2 possible tangents. Okay, it could hit there at 1, 1 or at 3, 9. So obviously up here 1, 1 is about there and 3, 9 is up here somewhere. So it's tangent up there as well somewhere. Okay, can't really see that. Okay, want to have a go, see what you think. Here's question 11. So here they give you a warm-up, reminding you if you're not knowing where you want tangency, you're coming from a point outside the line, you actually have to create the landing point. A, and then sub it in for the y value and use that. So it's an interesting algebraic trick. So you might try those there, and there are the answers there down the bottom. Alright, so what we'll do is just go back up to there and have a go, remembering if it's from a point you don't know where it's landing, you have to let that landing point for your tangent be A and f of A. Alright, we'll have a go, and we'll go on, and we're going to talk about, what's this? The second derivative. Well, could you find the derivative of the derivative? Would you be finding the rate of change of the rate of change? So you give it a double symbol, or y dashed, or what's called d2y by d2y by dx squared, because you're doing the process again. You're not actually squaring anything, by the way. Would it make sense? Well, I think so, because we said Newton had a displacement time curve, so it could have been something like this. So if he went ds by dt, the derivative, or s dash t, would have been 2t plus 3. Oh, that's a velocity. He wanted the instantaneous velocity, rate of change of displacement. If he did it again, let's do it to it again. What's that? That's the same as dv by dt. Finding the rate of change of velocity. Oh, that does make sense. That's the acceleration. So we can actually do the process again. Let's have a look at that. So here's an example, and we're not going to do much practical work at this stage with this. So if we have a function, first of all, change that to 3x to negative 1. You can do the derivative, and then you can do it again. Okay, so that's what they're talking about. Finding the rate of change of the derivative. And the obvious application for that is Newton's work. He wanted to find the rate of change of displacement to get velocity. Then he might want to know how fast the velocity is changing. That's the acceleration. So he'll do it again to the velocity function. Have a look at these. Have a go. Here are some answers for you. Just make sure you can do that process. So we've got a few more down here, doing it twice with different functions there in question 2 and 3, and we're gearing up to later on saying what could we do with that second derivative. Are there some applications? And there are some very good applications. So 3i, question 2 and 3, and have a go there. So the burning question is, where's this all going? Can we look at interesting applications of calculus with first derivative, second derivative? Where's that going? So they are interesting questions for a later presentation. So look, enjoy yourself. This has been a long road to getting you efficient, I suppose, in finding the derivative and all the things you can do with it. And we'll go on and have some excitement in seeing now that you are have that capability of applying it. So I'll catch you in the next presentation. At the moment, it's cheers from